Physics, High Level, Paper 1, Mock, 2016. A cube has sides of 10 plus or minus 1 millimeter. What is the percentage uncertainty in the volume of the cube? Well, how do we calculate volume? Volume equals base times height times depth. And because it's a cube, these three quantities are the same, 10 plus or minus 1 millimeter. Now the rule that you have to remember is because you are multiplying quantities, you must add the percentage uncertainty. So if we find the percentage uncertainty in this quantity, we would multiply it by 3, 1, 2, 3, to give us our answer. The percentage uncertainty in the length then would be 1 over 10 times 100, which gives us 10%. Because the base has a percentage uncertainty of 10, the height has a percentage uncertainty of 10, and the depth also has a percentage uncertainty of 10%, we add the three together to give us a total of 30%. Question 2. A toy car accelerates from rest down an inclined track at 2 meters per second squared. What is the speed of the car after 3 seconds? The first thing we must do is complete the quantities that we have using SUVAT, and also to list the equations of motion. If we complete our table, we can see that we have an initial velocity of 0, an acceleration of 2, and a time of 3 seconds. So it now comes to just choosing which equation of motion. We need v, and this is the simplest way to calculate that final velocity. As we know, the initial velocity is equal to 0, the acceleration is 2, and time is 3. Substituting the values will give us a velocity of 6 meters per second, which is answer A. Whenever doing this kind of question, an equation of motion question, it is fundamental that you complete the table for the given values and copy out the equations of motion so you have them in front of you, and it becomes really easy to just pick the one that will give you what you need. This is a slightly more challenging one. A parachutist jumps out of an aircraft and falls freely for a short time before opening his parachute. Which graph shows the variation of the acceleration A with time t of the parachute from the time he leaves the aircraft until the parachute is completely open? Now the first thing we need to consider is air resistance negligible initially? That means in that period before the parachute opens, do I need to consider the fact that I might reach terminal speed? Now, the question doesn't say anything about this, so you have to look at the graphs really carefully. If you do have to consider the fact that you jump out of the airplane, so here's our airplane, and you jump out of it, okay? If we do have to consider that there is some air resistance pushing up, then what would happen is that you would start with an acceleration of 9.81, but that value would decrease, and you would end up with a graph that looked like this initially, okay, as you reached a terminal speed. This is before your parachute started to open. Now we can see that none of these graphs do that. So the question seems to be leading you to this assumption that you don't have to consider air resistance at all until your parachute opens. Okay, now with that given, it becomes a little bit easier. When you first jump out of the aeroplane, your acceleration is 9.81, and it doesn't change until your parachute opens. So that can only be represented by graph B and graph C. So what happens now when your parachute actually opens? Now, if we consider forces, it might make that easier for us to think about. Initially, your parachute opens and you have a much greater force up than you do down. This means that there is a resultant force upwards, negative to the way that you were going earlier, and therefore you have, because force is proportional to acceleration, you now have a negative acceleration, which is slowing you down. That means that your acceleration goes from 9.81 to a minus value very, very quickly in order to bring your speed down. If you then consider what happens, eventually your forces will balance out. How do we know that they balance out? Because you eventually reach terminal speed. And at terminal speed, the force up is equal to the force down, which is your weight, okay? The force due to gravity. So in this situation, the net force equals 0, and therefore your acceleration equals 0. So the answer is B. You initially start with an acceleration of 9.81, which does not change until your parachute opens and you have a negative acceleration, which then decreases slowly to bring you up to an acceleration of 0. So the answer is definitely B. So here we have a forces on a slope question. It's definitely worth revising this, so I'll go through it very slowly. The question states that an object of mass m slides with an acceleration a down a plane, which makes an angle with the horizontal. The acceleration of freefall is g, so we can just leave g like that. What is the frictional force between the object and the plane? And there are two ways that you can be asked about friction. If you remember, the first one was using friction equals mu r, okay? And then the other one was summation of forces equals mass times acceleration. Okay, so we did that in grade 11. Now, there is no mention of mu in the answers, so we can forget that one. Don't need to worry about it. We're going to look at the summation of forces on that object. So I'm going to clean this up and I'm going to show you all the forces on here. So this diagram shows you the forces acting on the object. We have mg, which is the weight of mass m. We have this arrow here, which shows us the direction of this weight down the slope. So what we're going to have to do next is we need to find what is the component of this force down the slope. And we'll do that in a second. Now, because the object is moving down the slope, there is a frictional force opposing that motion, which is Fr, friction, and that's what we're trying to figure out. And we also have a reaction force. But the reaction force, to be perfectly honest, is useless to us because we don't need it. Okay, so let's try summation of forces. The summation of forces, by adding the forces acting along the slope, remember we're ignoring R because that's perpendicular to the slope. Now we don't need it anymore. So if you just look at what's going on here, we have, I'm going to call this force F. Okay, so we have F down the slope minus friction equals mass times acceleration A. Okay? So we now just need to find what friction is. But let's resolve force in terms of mg. How much of mg is acting down the slope? So now we need to draw some triangles, which I'll do now. So how much of mg is acting along the slope? Well, if you see this right angle triangle here, we have mg is the force and is the hypotenuse of this side here. So if we resolve along the slope, then F would be equal to mg cosine of this angle here. I'll call it alpha. Okay, so if we can figure out what alpha is, we'll know that F is mg cosine that angle. Now, what's that angle? If you now look at this triangle, it's apparent that alpha is simply 90 minus theta. Okay, so if we put that back into here, we have F equals mg cos 90 minus theta, or mg sine theta. Now, where does that take us? If we go back up here, f mg sine of the angle minus friction equals ma. By making friction the subject of the equation, I'll carry on, we'll have a little bit of space here, we have mg sine of the angle minus ma equals friction. So we just need to take mass out of the brackets, and we have g sine theta minus a, which is D. This is a really common question, so it's definitely worth taking a step back now and going through each step in this question until you're sure you understand it. A mass hangs freely from the end of a spring, so it's stretched out. So here we have the mass stretching the spring, so it's in tension. A student raises the mass vertically until the tension in the spring becomes 0. The gain in gravitational potential energy of the mass is equal to the work done. So this has been lifted up to the point where now there is no more elastic energy stored in here. Well, the answer is B. The student has done some work, force times distance, on the mass, definitely, because it's moved the mass m by a distance d. But in addition to that, the formerly stretched out spring has now lost that strain energy, okay, and that's basically gone into the system. Okay, so the answer is B. The gain in gravitational potential energy is equal to the work done on the mass by the student plus the elastic potential energy lost by the spring. So here we have a momentum question. An object of mass m moving with a velocity u collides with and sticks to an identical stationary object. Immediately after the collision, the combined object moves with a velocity v. What will be the loss in kinetic energy? Now, this is a complex question. They want you to do a lot for 1 mark. So let's just start with kinetic energy. Now, if we work out the kinetic energy lost, we would need to subtract the kinetic energy after the collision from the kinetic energy before. So what's the kinetic energy before? It's a half mu squared plus nothing, because the second object was stationary. Okay, so we only need to consider the kinetic energy of the first object. What's the kinetic energy after? Well, the objects combine to give a total mass of 2m, and their velocity is v. So it becomes a half times 2m v squared. These two cancel out, and we can simplify to give m on the outside a half u squared minus v squared, which takes us nowhere because that is not one of the options. What they want you to do is to combine the kinetic energy lost relationship with conservation of momentum. So you have to do 2 things now. Let's look at conservation of momentum. Using the conservation of momentum equation, momentum before equals momentum after, which is always true, we have the momentum of the first object, mu, plus 0, because that object has nothing, and then the total momentum after would be 2m v, because the 2 objects stick together. So what does that tell us? That tells us that if we get rid of those m's that coincide, u equals 2v. Now, the best way to approach this, maybe, is to consider all your options and then work through them. Let's see if this one holds true. This is in terms of u. So, if we rearrange this equation to give us the final velocity in terms of the initial, we have v equals a half u. Now, let's substitute that into this equation here. Okay, and what we're doing is we're substituting v squared for a half u squared instead. And if we expand that, we end up with m a half u squared minus a quarter u squared. So if we do that, if we get rid of a half u squared minus a quarter u squared, what we're ending up with is a quarter mu squared. Now, thankfully, the answer is A. Otherwise, we'd have to go through each to prove which one is the correct one. So that is a very long question, and there's a lot to do for that 1 mark. Okay, but once you understand it, it's very likely to happen again. A car is driven along a straight horizontal track. The car's engine produces a constant driving force. So F is constant. The car starts from rest, and the effects of friction and air resistance are negligible. Which graph represents the variation with time t for the power P developed by the engine? Now, power equals work over time, and work is force times distance over time. Now, d over t represents the velocity, but at the moment, so instantaneous velocity. As the car moves from rest and has a constant force, it then also has a constant acceleration. So therefore, this velocity will be increasing constantly. So if power equals force times velocity, and this velocity is increasing constantly, and this is staying the same, then we're talking about a linear increase, okay, where power increases as velocity increases. Right, on to specific heat capacity. An electrical heater of power 12 watts is immersed in a liquid of mass 0.2 kilograms. The graph shows the variation in temperature of the liquid with time t. What is the value for the specific heat capacity of the liquid? Now, this is a graphing question, and more importantly, it's a linearization graph question. That means we need to be thinking in terms of y equals mx plus c. Doesn't matter how complicated the relationship, you need to find the linear patterns. So let's have a think about the information we're looking at. We've got specific heat capacity, we've got power. Okay, so we know that energy supplied to an object that's increasing its temperature, okay, would be equal to the mass of that object, specific heat capacity, and change in temperature. But energy over time equals power. So therefore, energy over time equals power. Therefore, energy equals PT, power times time. So let's put that in here. Power times time equals m mass, specific heat capacity C, delta G. Now let's try linearizing this. So if I do my equation of the line, y equals mx, and there's no plus c because there's no intercept and there's no plus bit on the equation. So let's have a look. What's on the x-axis? We've got time. Time is on the x-axis. Okay, what's on the y-axis? Change in temperature. So I'm going to have to flip this around. So if I flip this around to make it look a bit neater, okay, so that's much better now. On the y-axis, we have temperature, but we'll see how easy it is to change that to change in temperature in a second. And we have time on the x-axis. Now, what does that mean? That means that our gradient equals P power over MC, specific heat capacity. Okay, so if we can work out the gradient of this graph, then it would be equivalent to power divided by mass times specific heat capacity. So let's work out the gradient. We have 26 minus 20, which is this height here, over 200. Check the units just to check there's nothing funny going on. No, everything's really straightforward. And we end up with 6 over 200, which equals 0.03. Right, so that's the gradient. So that's equal to 0.03, which is equal to power. Now the power is 12 watts divided by the mass, 0.2, times our specific heat capacity. So rearranging all of that to find specific heat capacity will gives us an answer of 2,000 joules per kilogram per Kelvin. Now it seems really complex, but this is a very common question. So it will either appear in multiple choice or in paper 2 or even in paper 3, because this is one of your practical required practicals. So work through this again if you have to. Make sure you understand the linearization process. Or see me and I'll explain it to you personally. Question 9. Why is wave-particle duality used in describing the properties of light? The correct way to answer this question is to look at each answer individually and see if it's a complete answer. A, light is both a wave and a particle, is a very vague statement. Is it both a wave and a particle at the same time? Not necessarily. This is a very simple and incomplete picture. Both wave and particle models can explain all the properties of light. Well, if they could, we wouldn't need both of them, would we? So what we need is something a little bit more specific. C, different properties of light can be more clearly explained by using one of the wave or particle models. Now this is a more complete and specific picture because it really just depends on what property we're talking about. If it's reflection, if it's refraction, interference, each individual one would have a particular particle or wave model. So the correct answer is C. Two separate sealed containers hold air at the same temperature. They are connected by a thin tube containing a valve. So it's almost like having two separate containers. Initially, one container holds 0.2 meters cubed of air at a pressure of 50 kilopascals, and the other container 0.3 at 20 kP. The valve is slowly opened and the temperature stays constant. What is the final pressure in the containers? By opening up this valve, in effect, we're releasing the gas so that it redistributes itself. The total volume afterwards will be the same. It will be 0.2 plus 0.3. So that will be the new volume, but what will be the new pressure? The best way to consider this would be to remember that the pressure times the volume relationship before is going to be equal to the pressure and the volume relationships afterwards. So what is the combined pressure-volume relationship before? If we consider each container separately, and then add them together, the combined pressure-volume relationship would be 0.2 times 50 plus 0.3 times 20. After, the volume is 0.5. So here, if we make volume the subject of the equation, rearrange, and we end up with 32 kPa, which is our answer. Simple harmonic motion. In simple harmonic motion, the velocity leads the displacement by a phase angle phi. What is the value of this angle? So let's have a quick review of simple harmonic motion graphs. Now these graphs you definitely need to learn off by heart. A displacement time graph would look like this, but better, obviously. If we consider the velocity of this displacement time graph, velocity is equal to the gradient of a displacement time graph. So let's have a look at what's going on with the gradient of this graph. When displacement is at a maximum, we have a gradient value of 0. Then we can see that the slope increases but in the minus direction and reaches a maximum as it goes through the origin here. So if we just draw that, what you can see now is our velocity time graph in green starts at 0 and then drops to a maximum when the displacement is going through 0. Now you can see here that the gradient starts to decrease again to reach 0 here. So if I complete that graph now, or we'll try, we end up with this pattern, which repeats as we go up. And looks like this finally. Now this is just revision. Now we need to answer the question, what is the phase angle difference? Well, if you remember, an entire circle is equivalent to 2 pi phase difference. And we would represent that on a graph as an entire cycle of difference. So if something was 2 pi out of phase, then it would look exactly the same as this, but it would start an entire cycle later. So let's have a look at this. We have from here to here, it's almost as if this velocity time graph is lagging, but how much of an entire cycle? From there to there, we're talking a quarter of a cycle, okay? There is a quarter of an entire wavelength lapse. So a quarter of 2 pi would be pi over 2. So the answer would be a phase difference of pi over 2, which is C. Definitely worth paying close attention to this topic, as there are no questions on this on the specimen paper, which makes me rather suspicious that it might come up in paper 2 in the real thing. Now to sound. Which of the following, if any, will be transferred in the direction of propagation of a sound wave as it passes through the air? Now, if you remember, propagation of sound is due to rarefaction and compression. So what happens is the sound travels by squeezing the particles together and then stretching them out again. However, these particles, they simply vibrate backwards and forwards. The particles in reality do not move beyond their equilibrium point. Okay, so mass is definitely not transferred, and in fact it's actually a definition question. Waves transfer energy only. Okay, so the answer is B, as these particles do not vibrate beyond their equilibrium point. On to Newton's third law. A metal sphere is at rest on a bench. According to Newton's third law of motion, what is the possible action-reaction pair for this situation? So if we have a ball on a bench. So Newton's third law, forces are always equal and opposite. So what do we mean by equal? They are of equal type. So before we start reading the answers, must remember that if we're talking about gravitational forces, then they will both have to be gravitational forces. If they're contact forces, they'll both be contact forces. And then the second thing to consider is that they are opposite. What does that mean? That if you have two objects, say a sphere and a bench, A and B, then the Newton's pairs would begin with A acting on B, and then the reaction force would be B on A. So let's have a look at the answers we've got. Could it be A, the downwards gravitational force of the Earth on the sphere against the upwards gravitational force of the sphere on the Earth? Now this sounds pretty good because we've got both the same type, equal, but opposite, because we're going from Earth on sphere, object, B on A, and now sphere on Earth, A on B. So I think pretty clear it's A, but let's have a look at the others. Could it be the upwards gravitational force of the Earth on the sphere, or the downwards gravitational force of the sphere on the Earth? It could be, but it just happens to be nonsense. How can the gravitational force of the Earth on the sphere be upwards? That would mean that the sphere went flying upwards, which it clearly doesn't. C, could it be the upwards electrostatic force acting on the sphere due to the atoms on the bench? Could be, but what's the reply? The upwards gravitational force. That cannot be right because it's a different type of force. Similarly, in D, it can't be D because we've got an upwards electrostatic force against a downwards gravitational force. So no, the answer is A. A high solid wall separates two gardens X and Y. Music from a loudspeaker in X can be heard in Y even though X cannot be seen from Y. Music can be heard in Y due to, well, this is to do with sound travelling around corners. And that's to do with the relationship between the gap and the wavelength, which you should remember from last year was diffraction. That's the basic definition of diffraction, being able to move around corners, or waves being able to travel around corners due to their properties. Question 15. In a particular lightning flash, a charge of 15 coulombs flows in a time of 0.5 milliseconds. Careful with units, I can see what's coming. What is the average current? Well, the definition of current is charge over time. So if we work that out, we've got 15 divided by 0.5 times 10 to the minus 3. Don't forget that. So we end up with 30,000 or 30 k amps, which is a huge amount, but it is a lightning flash. 16. A heating coil is connected to a battery of EMF 10 volts and negligible internal resistance. The power dissipated in the coil is 25. What is the resistance? Well, that's just a simple power resistance relationship. So we've got power equals, let's see, we've got voltage and resistance, V squared over R. So if we work that out, okay, if we rearrange to make resistance the subject of the equation, we've got resistance equals V squared over power. V squared, we've got EMF of 10 volts, so 10 volts squared is 100. Power dissipated is 25. 100 divided by 25 gives us a resistance of 4 ohms, which is C. Sticking with electricity, we now have two identical cells, each of EMF 1.6 volts and internal resistance 2 ohms. These are collected in parallel with a 3 ohm resistor. So this is our circuit here. Now again, this is quite a challenging question. It really requires you to work hard, but I'll go through it. The best way to answer is to consider Kirchhoff's laws. Okay, now we need to label everything sensibly so it makes. So let's consider the circuit now. We've got three currents. The current flowing through the main resistor, okay, which we'll refer to as I1, and the potential difference across that main resistor. And then the two power supplies, the cells, they're each 1.6 volts, but of course this one, number 3, has a current of I3 going through it, and a potential difference across the internal resistance of V3. Similarly, we have a current of I2 going through this branch, and the potential difference would be V2. Okay, so let's look at Kirchhoff's first law, which is to do with current and junctions. So if we think about this junction here, Kirchhoff's first law states that the current flowing into a junction would equal the current flowing out. So we can express that as an equation. Okay, so here it is. The I3 plus I2 equals I1. Okay, and that's the first of many equations. So now let's think about Kirchhoff's second law, and that was to do with closed loops. So we have two loops that we're going to consider. This one first, and then secondly we'll look at this one here. Now, what do we mean by Kirchhoff's second law? Kirchhoff's second law is the power, the EMF into a circuit will equal the power out. It's quite easy if you think about it in terms of energy. The energy given to the current by the power supply would be used by the two resistors. So this energy would be used by this tiny resistor here, well not so tiny, and this one here, because the current flows round in that loop, collecting energy here, losing it here and here. So in effect we have 1.6 equals V3 plus V1. So let me write that down. Okay, so V3 plus V1 equals 1.6. Now we need to bring it back to current eventually. So we can now use voltage equals current times resistance in this equation to bring in our current terms. So let me substitute these values in, considering that V3 is actually equal to current times resistance. So it would be V3 would be equal to I3 times 2. So 2I3 plus, and V1 would then be equal to 3 resistance times current 1. Okay, and that would be equal to 1.6. Now that was our first loop, and that is now our second equation. But we had another loop, and if we think about it, it would be exactly the same. But instead of I3 and I1, we would end up with I2 and I1. And the values are exactly the same, so it's just a repeat. So we now have three equations. The first one, Kirchhoff's first law, and then equations 2 and 3 come from Kirchhoff's second law. Now what we're going to do is we're going to substitute equation 2, and 3 into 1 by making I3 the subject of the equation here and I2 the subject of the equation. So let's do that. And if we do that to equation 2, we will end up with I3, current 3, equals 0.8 minus 1.5 I1. Why? Well, I made I3 the subject of the equation, subtracted this from here, divided it by 2, okay, and I ended up with 0.8 minus 1.5 I1. And this would do exactly the same. So if I rearrange this equation, I would also end up with I1 being equal to the same thing. So in fact, I'm going to write that there. Sorry, not I1, I2 equals I3, and it equals, so both equal 0.8 minus 1.5 I1. So now I've got that fourth equation. I'm going to substitute that fourth equation in here to the first one again. So if we substitute them in, we ended up with 0.8 minus 1.5 I1 plus 0.8 minus 1.5 I1 simplifies out to 1.6 minus 3 I1 equals I1. And finally, 1.6 equals 4 I1, which gives us a current of 0.4 A, which is our answer, A. Now that is a huge amount of work to do for 1 mark, but sometimes questions are just really, really hard, and you don't have to feel bad if you don't get them right. These are one of these questions that you should always leave to the end if you happen to have some time left over. Back down to earth to something a little bit more straightforward. We have 4 energy levels for a hydrogen atom with their corresponding energies. Now, when an electron changes from level 6 to level 1, the spectral line has a wavelength of 9.4 times 10 to the minus 8. What is the approximate wavelength of the spectral line emitted when the electron changes from level 4 to level 2? So let's go from level 4 to level 2. What do we end up with? Okay, so this would give us a net difference of 4 times 10 to the minus 19 joules. Okay, if we remember that the energy in a photon, which would be what's emitting the frequency of light, equals hf. So if we divide this energy by Planck's constant, we can end up with a frequency of about 6 times 10 to the 14. So F would be equal to 6 times 10 to the 14. However, we have speed equals frequency times wavelength. So we now need to divide the speed of light, 3 times 10 to the 8, by 6 times 10 to the 14, which gives us approximately 5 times 10 to the minus 7. Okay, so the steps are the following. You find the energy difference. Remember, it's a scalar, so the sign isn't that important. You just need to find the difference between the two. And that gives you the quantity of energy in joules. You use the fact that Planck's constant specifies the amount of energy in a photon. So energy E equals hf to find the frequency of light. And then you use the standard wave equation to find the equivalent wavelength. Right, the next question. The magnitude of the binding energy per nucleon is, well, we have to look at each of these sentences individually to see which one's correct. If we think about the magnitude of the binding energy per nucleon, it's best represented on a graph, okay, a binding energy per nucleon graph, which peaks, if you remember, at iron. I should just write Fe, it's easier, okay? Now, is it a maximum for nuclides having a nuclear number around 60? Well, that's true, because we are talking about iron, Fe. Is it directly proportional to the neutron to proton ratio? Well, that's not true, because what that's saying is that it's relevant to the number of neutrons and protons, and that's a different graph. That's the NZ graph, which has that bit in the middle, if you remember, showing you the kind of decay that you expect. So we'll disregard B. C, a maximum for nuclides with high nuclear charges. Well, that's not necessarily true, because it's saying that as the atom got bigger, you would have the binding energy increasing, and that's not actually true. Remember, it peaks in the middle and then comes back down again. And then, is it a maximum for nuclides with low nuclear charges? Down here, is it a maximum? No, it's actually lower. Okay, so the answer is A. Okay, it's basically peaking here at the iron size. Okay, question 22. A positive pion is a meson consisting of an up quark and an anti-down quark. A student suggests that the decay of a positive pion is represented by the following equation. The suggestion is incorrect because one of the quantities is not conserved. Which quantity is not conserved? Okay, so again, if we go through each individual one, the one that stands out immediately is a lepton. As you can see, we have a neutrino here, which is a lepton, but it's only on one side of the equation. So immediately we can see that the lepton number cannot be conserved because you can't have a lepton on one side. So here we have our, sorry, it's not a neutrino, it's an antineutrino on this side of the equation. Okay, so this question's about Sankey diagrams. If you remember, Sankey diagrams show you how energy is distributed. So here we have the energy in for a fossil fuel plant of efficiency 40%. Now, efficiency of 40% means that 40% of all of this energy that comes in is going to be wasted, or rather than wasted, as it says here, lost through frictional, electrical transition and energy losses to the lower temperature surroundings. So the question, which branch represents these energy losses to the surroundings? Well, if we consider that 60% is energy that does not get used effectively, okay, so which would represent 40%, D. D would be the 40% which is useful, and then we're left with these remaining 60%. The energy loss to the surroundings, we would expect it to be the largest chunk of energy loss, okay, which would definitely be B. Electrical transmission is a smaller piece of the picture. That might be A or C. They seem about similar. Similar with frictional energy losses. They'll be minor. Considerable, but still minor. And energy loss to the surroundings would definitely be B. 25. What is the thermal conduction mainly due to in a gas? This is a very basic definition question. So we'll look at each individual answer. Could it be due to the motion of free electrons? Now, this would be the case if we were dealing with thermal conduction in a solid, but we are not. In a gas, the motion of all particles is relevant, not just those free electrons. Could it be fast molecules transferring energy to slower molecules? Well, definitely, because until those relative energy levels balance out, so every molecule has the same amount of energy, this would continue to happen. So this is a definite possibility. Could it be slow molecules transferring energy to faster molecules? Nope, because that is ridiculous. That just doesn't happen. And lattice vibrations causing collisions. Well, that can't be the case because lattice vibrations are associated with solids. So the answer is B. Projectiles. The diagram shows the trajectory of an object projected in the absence of air resistance. So this is the standard image we're used to seeing. The object is then projected with the same initial conditions, but this time air resistance is taken into account. How does that then make a difference? Well, if you have air resistance, then acceleration would be affected. Vertically, not only would you have, the object would be moving up, and not only would you have the weight of the object pulling the object down, but you would also have air resistance countering motion. So you would have a value greater than minus 9.81. it wouldn't go up so high for a start. So let's have a look at the options. This one is a possibility. Well, they're all. This is definitely not going to be a possibility. But these three definitely are options. So now let's have a look at what's going on horizontally. Now, very typically of projectile motion, where you have the initial equals the final velocity, well, that would definitely not be the case anymore. And you would have a slower, you would have a velocity decreasing as you move forward, and then you would lose this symmetrical shape. So that wouldn't be a case anymore. And the second half of the journey would definitely be much shorter than the first. Okay, so if we look at all the options, it looks like B is more plausible. Okay, so a reduction in height, a reduction in range. Let me rub that off, which is a bit of a mess. Okay, we have here a reduction in height and a reduction in range, and the loss of this kind of symmetrical picture, as the second part of the journey is much shorter than the first. So on to quantum physics and radioactivity, and we have the work function of a metal. And what does that equal to? Well, if we think back to Einstein's equation of photoelectricity, we have the kinetic energy that's left over in an electron that escapes a metal is equal to HF, the photon energy, minus this work function. If you remember, the work function was the amount of energy that had to be paid, in effect, in order for the electron to escape. It's like the minimum payment of energy it needs to get out of its lattice structure. So let's have a look at the options that we have. Could it be the greatest energy with which an electron can be ejected from the surface? So could it be the largest amount of energy it has left over? Well, that relates to this amount here, and it's definitely not that, okay, because that's what it's got left over. So it's not A. Could it be the least energy with which an electron can be ejected? Now, what we mean by the least energy with which an electron can be ejected, it would be when the photon energy, HF, it's not working, HF equals the work function. So if you can imagine an electron receives a photon just enough to escape, but it doesn't really have any energy left over, okay, that would be the least energy situation. So Ke would be equal to 0. The least energy with which an electron can be ejected would be a tiny minimum amount, barely 0, okay, when the photon just enables the electron to escape. So it's not going to be that one. Could it be the difference between the energy of a photon incident on a surface, HF, and the energy of the least energetic electron ejected? So that's back to this idea of the least energetic. But that could be 0. Like, that's the least possible energy you could have. So is it HF minus 0? No, because that would leave the energy of the photon. That doesn't give us the work function. So let's have a look at D. That's not C. D, the energy difference between the energy of the photon, HF, on the surface, and the energy of the most energetic electron. So could it be HF minus the energy of the fastest electron? Well, if we look at the equation above, if we see HF minus Ke, it does in fact give us the work function. So the answer is C, definitely. And if we think about that fastest possible electron, that's going to be the one that's escaped with the most energy left over. So therefore, what you've worked out is the minimum possible work function. Okay, what is the absolute minimum work function energy that you must provide? So it's definitely D. Okay, question number 8. The density of the material in the nucleus of an atom, and you've actually done this proof yourselves where you worked out the volume, the mass and the volume of a sphere to find that the nucleus, the density of the material, mass over volume, is always constant. Okay. Does it depend on the number of nucleons in the nucleus? It doesn't only depend on the number of nucleons. The number of nucleons would affect the mass, but it would also affect the volume. Okay, so it's not just the number of nucleons, but it's also the volume of the nucleons. And it's definitely not going to be dependent on the number of protons and the number of neutrons, because this would only be half the story. You would definitely need to consider the entire mass, that means the nucleons, but not just the mass, you'd need to consider the volume too. So the answer is A, because as that mass increases, so does the volume, and it tends to balance out in the end. Question number 9. A narrow beam of electrons passes through a thin crystalline film in an evacuated tube. A series of rings appear on a fluorescent screen at the end of the tube. What phenomena within this film explains the observation? Well, we've gone through this, and it's a diffraction of electrons. Okay, and this is one of the groundbreaking experiments that we looked at just before we started talking about de Broglie, the de Broglie formula. And the last question, in radioactive beta decay, beta particles are emitted in a continuous spectrum of energies. This is because during energy changes, beta particles share the energy with neutrinos. So this should be clear and obvious from the beta decay equations, where neutrinos are always present. Okay,